Right now, you might have a video playing, a music app running, a word processor open, and dozens of browser tabs suspended in the background. To your computer, every single one of those tasks is a process. A process is a program in execution, made up of its code, a stack, and a heap. And there is a hard law in computing. For the processor to actually run that code, the process must physically reside inside your RAM. Add up the data required for all those open applications, background tasks, and the operating system itself, and you're easily demanding 30 to 40 gigabytes of active memory. But pop open your laptop, and you might only have 8 or 16 gigabytes of physical RAM chips actually soldered to the motherboard. If your software was forced to rely strictly on the physical hardware you actually own, your computer would run out of space and crash within seconds of booting up. Early computer engineers tried a literal approach called contiguous allocation. They took an entire program and stuffed it into the physical RAM in one continuous, unbroken block. This diagram demonstrates a fatal flaw. When apps close, like Process 8, they leave scattered empty blocks. Here, we have enough free memory to load a new process, but because that space is chopped into non-continuous blue gaps, it cannot physically fit. This is external fragmentation. Adhering to the strict physical layout of the memory chips ruined multitasking efficiency. To fix it, the operating system had to step in and start lying to the software. The solution was separating memory into two distinct realities: the physical address space, the actual silicon, and a fabricated logical address space. The operating system tricks every application into believing it has a flawless, continuous block of memory to itself, starting right at address 0. This schematic shows the hardware device that pulls off the trick, the Memory Management Unit, or MMU. Sitting straight between the CPU and the RAM, the MMU catches the logical address generated by the processor and physically alters it into a real, physical location. Every single application operates in total isolation, unaware that the MMU is secretly redirecting its data on the fly. Early systems tried breaking programs apart by logical units, like separating the stack from the heap in a method called segmentation. But the ultimate solution to the fragmentation problem was something much more rigid: paging. With paging, the physical RAM is secretly chopped into thousands of fixed-size physical blocks, usually about 4 kilobytes each, called frames. Simultaneously, the program's continuous logical memory is chopped into equal-sized pages and scattered into random open frames in physical RAM. To track this, the OS uses a page table, checking it to find which physical frame hides the requested logical page. Standardizing the block size completely eliminates external fragmentation. Because all pages and frames are the exact same size, if there are free frames anywhere, the OS can run the program. But hiding the truth creates a massive performance bottleneck. Because the page table lives in the main RAM, the CPU has to access memory twice for every single instruction, once to read the map and a second time to grab the actual data. This mandatory double read cuts the computer's processing speed right in half. This diagram illustrates the hardware fix built to solve that crisis, the Translation Look-Aside Buffer, or TLB. It acts as a fast-track bypass route, avoiding the much slower trip to the main page table at the bottom. The TLB is a hyper-fast associative cache. It remembers your most recent page translations and instantly provides the physical address. Without the TLB doing this heavy lifting, the grand illusion of infinite memory would make your PC too slow to actually use. Engineers track a metric called effective access time to measure this delay. Because the TLB successfully finds the translation, a hit, between 80 and 99% of the time, the delay penalty of checking the main page table is virtually erased. But what happens when the physical RAM frames are 100% full? This schematic shows the emergency safety net called swapping. The operating system secretly exiles inactive pages from main memory out to the much slower hard drive, the backing store, to free up RAM. It only recalls them when you click back into that specific application. Between the blinding speed of the TLB and the emergency storage space provided by swapping, the operating system maintains a flawless, uninterrupted experience regardless of your physical hardware limits. Every time you switch a tab, you trigger millions of page translations, TLB hits, and memory swaps in a fraction of a millisecond. We often view our computers as limitless canvases of potential, but they are actually engines of strict limitation. Modern computing relies on a microscopic bureaucracy and operating system, lying to the software millions of times a second to keep the illusion alive.